Okay, so before I moved to the US, I worked for the European Sound Observer. That's not ESO, but ESO. And I spent probably most of my career building control systems for scientific facilities. In this case, it was large optical ground-based telescope. And I spent a lot of time in Chile, and since it's an international organization that is funded by the member countries, there's always if there's some critical event, high profile, people are coming to visit and see how we use their money. And I was there, and I was like 26 or 27, and the Prince of Spain and his delegation came, and I was supposed to give him the demo. I always say it's the King of Spain, but actually it was the Prince. Anyways, I prepared everything, in the morning they flew in with the private plane, landed in the dust, and tested everything in the morning, scripted all on how we slew the telescope and move around, because it's very impressive to have like 400 tons of steel and glass moving around at high speed. And the demo, or should be, or was scheduled for after lunch, so I went for lunch, quick lunch, went back, tried again, didn't work. The telescope initialized and slumped down 30 degrees, and I could not figure out what the hell is going on. They were already in their cars. At some point, I found out that after I tested everything in the morning, I changed something else somewhere else. So it should not have any impact, but it did. I rolled back. Fortunately, we had version control, did the demo, the Prince was happy, they left. So what was the problem? We did not have any systematic qualification. The heroic effort, which is the usual thing, is figure out all the systems to get it to work. But if something breaks, then it sucks. So that's what the topic of today's talk is around. How can we systematically qualify systems, right? And what are we trying to do at JPL for space missions? So let's go there. So I have a lot of slides and not much time, so I will skip through the not so interesting ones. JPL is NASA and Caltech more or less at the same time. They're funded. The oversight is done by Caltech. NASA gives us the direction, and then they negotiate the contracts. So what we are supposed to deliver. What do? We land on other planets, basically. We fly to them. But for that, you need a lot of system engineering. The teams are huge, and it's not some single or small team effort, but you need usually a teams of systems engineers that guide that collaborative design for those really complex technical systems that get more and more complex. So those systems engineers have to provide leadership, right? So they have to support their team, run around, follow up. They are responsible for architecting and designing the cyber-physical systems and to manage their complexity. So this is somehow what we understand under the term systems engineering. What you see here, so that's at JPL, that's the team of Perseverance, so that's the latest rover that we landed last year. So the teams are getting bigger and bigger, right? And unfortunately, they still communicate a lot through spreadsheets, in particular system engineers in engineering level. So Excel engineering. So who of your organizations use Excel for system engineering? None. Wow. Okay, there you go. So there's a lot of spreadsheets, and then not only spreadsheets, also PowerPoint and email in particular, sending different versions of Excel sheets around, and then someone, typically the system user, had to kind of figure out what's the right thing in order to do this in the end, right? So, but to do this, we have to do a lot. And so how do we get from that to that? So it takes a lot of people, requirements, spreadsheets, documents, processes, and so on, in particular a lot of people, and heroic effort, as I mentioned before, to get there. And we have, during that process, from, say, the early phase of the project to the actual launch and landing, a lot of silos are created, right? There's no systematic approach, and a lot of duplicate work. So usually it starts very simple, right? There's some models and spreadsheets, people present it in PowerPoint, but as people go along and add models, because there are models, of course, in one way or the other, formal or not formal. So they add more information and add it in the document. We publish documents, of course. The main product of the system engineer is still a document in the end, right? And it gets complicated very quickly. And we have this really bad ratio of actual engineering work and the overhead, right? So there's always some repetitive data entry. There's where is the right version? Is this the right email or that? Or there's some DocuShare repository somewhere, which is even more scary. And there's this constant searching, right, for that information that we need, right? Either looking on some drives or in emails or in asking people in the end. So how do we get and connect all these things together? So for the mathematicians among you, dragons and monsters might mean something, but it doesn't really matter so much. But what we mean by the monsters is that they appear, right, as we develop our system, right? So with more functions, more hardware, more software, we observe that these silos somehow create by themselves and occur and reproduce themselves. So in our example, it would be like flight software, ground data system, and the remote engineering unit. So they are disconnected. And but they have implicit connections, right? So it's really hard to understand what those relationships are, right? And for example, how to check requirements against the test and perform impact analysis. But with models, and that's kind of so my team provides this whole digital ecosystem to support all those systems engineering tasks and for analysis and engineering in a traceable, connected way. Not perfect, but we're getting there. It's much better than 5 years ago. But we can resolve those monsters by capturing those relationships, so they cannot hide as much anymore behind the silos. That's the escape room, actually. I wonder if there are some monsters. So they live in a discontinuous space, right? There is usually among us overhead to connect everything manually. So it's very difficult to break those silos. Right? It's disconnected and implicit, specifically with Excel. It's fractured, and the biggest problem is that the qualification process, if we have to qualify the system for flight, is not systematic. Right? It's basically like chaos most of the time. Surprisingly, still land. I don't know. So what we're trying to do is to tackle that with what we call digital twin pipelines that evolve with the system's development from the early phase to the delivery. So we have this visualization shows you. Let's see. So we see the systems development life. Oh no, it's cut off. I see there's a spiral with intermediate milestones, right, as the system evolves. And for each of those steps in the life cycle, we create a digital twin. And these are the fractals. So we start with a very simple digital twin. It could just be an architectural model. But as we go on, right, they increase in detail, they increase in fidelity, and we learn more about our system as we progress towards the implementation. The qualification is a property of those twins, right? So we connect the twins, so when we go from one to the next, only when it's qualified. So there must be some test or some qualification. And the life cycle axis, which is the red thread from here, is how those twins connect up. Right? So we start very simple, we evolve them, so every time we add more details to the fractals here. And in the end we have the dragon, which is that fractal. So that's the vision. Right? This is what we want to achieve. To have a systematic qualification process throughout the system development lifecycle, supported by models. So what we do is we project that spiral of system development into this fractal pipeline, right, with increasing detail and fidelity, and we have some degree of comprehensiveness for each of the twins, right? So they have to be qualified, and each twin, each pipeline builds on top of each other. And the pipeline could be, for example, I build an executable model, and I have a test that verifies that the executable model, for example, satisfies the requirements. And that can be in a very early phase of the project, right? And it could be very simple. But as we progress, we add more and more detail. So we expand those pipelines over time, and we manage also the change packages. So there's always configuration management and version control as we progress. So we can go back at any point in time to see what happened and see what the impact was and why something doesn't work anymore, or it should work. The fractal approach is that each qualification step remains valid over time. So the model and the test that are built very early should still work at the end. And I've had all these details added, right? So that nothing should ever become invalid as we progress in this spiral. So what we should get, and here comes the dragon. So the architecture that we call that the dragon architecture, because the dragon is this fractal thing that beats the monsters. Because the monsters, I mean, the mathematicians probably know better. I'm not a mathematician, but the monsters, before people understood what fractals are, they called them monsters, and then the dragon was the one that defined them mathematically. So we have an explicit qualification record through that process, right? So if an auditor comes in and we make a change, we have, or we will have, at the moment we have pieces of that, right? But that's the vision, that we can present an explicit qualification record that is auditable, right, over the development of the system. We have the relationship between these representations, so the progression, and there's a systematic process for developing that system. So this very colorful slide is the dragon architecture. So it's a kind of a combination of the ecosystem that we have with all the applications and services. So we have, and here it's like just a snapshot. We have about in our ecosystem around 35, 40 applications and services that are integrated to support the whole system development lifecycle, model-driven, and that we have built over the last 5-6 years. This one is kind of our workflow, which is iterative. We have 2 environments, but that's more an organizational split. But it's really one environment for software and systems. And you see the dragons the monsters are hiding here, right? But through the process and through the infrastructure, we connect those silos, right? And we break them up, or they don't even get into existence in the first place. I won't go in all the details, but you'll see we go from requirements, design, architecture, testing, model checking, analysis with system tests and so on to the publication and the change package management. Important, since we talk about systems engineering, document is really at the end of the output. One very important part is to keep that document, that textual artifact, in sync with the engineering models. Right? So there's another product we'll talk, or enabling technology, which is OpenMB, that enables that kind of connection, to close that disconnect between engineering work and the system engineering document, which is a whole other slide, right? But maybe a discussion for one of the working groups. So what are some examples of that dragon architecture? The very first one, which we did like maybe 1.5 years ago, is a kind of a mini pipeline, and you will say, well, that's very simple, and exactly the point. It should be simple, right? And something is so obvious, and people think of model-based system engineering as like, I need this very complicated executable model and SysML. No, In this case, people had requirements and they did some tests and they were disconnected. And the remote engineering is a critical element in flight. That, for example, handles the clock and the fault protection. And the problem was that people wanted to test things and show that they tested the hardware and that it satisfies the requirements. So what we did, we used hard parts of our ecosystem to actually establish that traceability, which is, again, sounds very stupid, but having that traceability in a model-based way, so it's making these relationships explicit, queryable, and checkable, we could now generate reports, we could query them, right, and we had some systematic thread, and we could analyze if we had a requirement that was not connected, or a test that was not connected, or a test suite. Right? And it sounds really stupid, but in the end, that was a huge, compared to Excel and email and giving someone a call, it made a huge difference. We have a few other pipeline prototypes. So we have a lot of those pieces, and we started to build those, the infrastructure to support those pipelines. One other example is model execution and test. And again, you see the monsters are over here, but through the ecosystem and the infrastructure that we have, we connect those pieces, right? So we will have the requirements, you have some executable model, you have some traces that you test scenarios that you where you test the model, for example, and you generate code, right? So the ecosystem keeps that traceability. One thing changes, it trickles down all the way to the code generation. And if you look at the code, you can trace it back to the model. Code generation is a major thing. At JPL we have done it in a while, but it requires some improvement. I've done it, as Daniel mentioned before, at ESO for starting around 2005, I think, or 6. And again, the monsters are here, and we kind of resolve those monsters by connecting the requirements, the generated code, the generated test code, and the test output, right? So that you have, whichever piece you look, right, you're able to query it, validate it, and report on it. So for example, you would generate the application code from the model, but also the test code. And connect it with, so you could create the model of the test code, but you could also use some model checking facility to have, like getting a trace from a model checking run and use that to generate the test code. So you have all the things that you resolve in the model. If you have some problems in the model that you find with model checking, we would use that trace to generate the test code. Document generation is another example of a pipeline. So what people want to do, the software developers, they have to kind of, they have to demonstrate that their code satisfies some requirement. So what we do is, or what they can do is, they put a link to that requirement into their code, but we parse the code, analyze it, and establish automatically in another service that traceability that is again queryable, validate, and we can validate. So by supporting that, because what we want is to automate as much as we can, right? So people make a lot of mistakes when it's done manually. So we try to support where we can the developers, system engineers, whoever the engineers are, with some automation, automated infrastructure. So we would auto-include those links into the code and generate, for example, the documentation of that code that links back to the requirements. So you see the code documentation, and you see also, okay, this is the requirement that is actually satisfied, and that is generated. So what are the enabling technologies in this, or some of them, or the main ones in this ecosystem that we have? So this is the kind of life cycle that we have, a workflow for the systems. This is all iterative, right? So we have these phases of collaboration capture where we set up the architecture topology, we discover the elements in the system, the components, we capture design and constraints, and we deconflict things. Right? So in the beginning, in particular, there's a lot of things that are overlapped, conflicting. So the point is to help the system engineers to deconflict those architectural elements. Once you have set up that topology, we have recently, like a couple of months ago or a few months ago, started using into generative architecture exploration, which kind of changes the picture quite a bit. So you would generate architectures from your architecture space, perform system level multiphysics co-simulation. So that actually works quite well, where you do kind of functional traits with generative architecture, project it into some physical space and run there some, for example, modelical simulation. And then you iterate over that whole cycle. We would specify behaviors, variants, and configurations, and then perform analysis, quantitative analysis for compare different attributes, evaluate constraints, visualize different things, like you would run the multiphysics simulation, visualize the telemetry like temperatures or battery state of charge and so on. And you can perform those functional physical traits in an iterative way. And in the end, produce some products, the publication thing, the documents in particular at the system engineering level. So one key element in that is OpenMB, that maybe you have heard about. So primarily OpenMB is a community, right? It's a community which share all a common goal. All those organizations want to establish some model-based engineering environment. Right? I have started that community maybe 7 years ago. We had several workshops at INCOSI and the MONUS conference. It has grown significantly. We are at 498 members now, so we'll update that once we hit the 500. But there has been quite a few substantial organizations contributing, participating. Okay, us, Boeing, Lockheed Martin, OMG, Naver, Ford, Stephen, and so on. And this kind of one main thing is kind of this diagram where we want to have linked data documents. So one of the products that the community creates is to enable those linked data documents. So I have a document that directly embeds and dereferences engineering models in a narrative text. So whenever the models update, the document would also be updated. We get a consistent, not only the document is consistent within itself, but it's also consistent across all the documents that you generate. Right? So we update once, and it's reflected everywhere. And that we have quite a bit. So there's a whole other presentation about that, but yeah, that has been quite successful. So the community contributes and creates software, but also contributes models, and it's basically a forum to exchange ideas. We have bi-weekly meetings with the community, and we have leadership meetings. So I invite all of you to join that. It's a fun group. So the vision is, and there is a question yesterday, discussion yesterday, what is our central piece in the architecture, not only at JPL, but in general, and that for the last few years somewhat crystallized with Jupyter. Jupyter has become, or the Jupyter environment has become like a central pillar in this model-based engineering environment because of its multi-language analysis capabilities that we can connect with engineering and modeling. So it serves as, in the future, also for system modeling with SysMLB2, which is supported in Jupyter, but it kind of becomes the center hub of accessing requirements, system models, drawing information from them, processing them, and pushing it back to the repositories, and enables also automation. And it's very popular. We have more than 600 users, Jupyter users at JPL, and people adopt it very quickly, surprisingly. So we want to provide all that as a service. So it's MBSE as a service. So we provide not only the infrastructure, but also the people to help to use that infrastructure. And we create basically a commodity. So it's not that the project has to figure out how to put all these things together, but it's there, ready to use, and they can focus on the engineering work. This is the most important thing, right? People don't want to get distracted by installing things and figuring out how to integrate. They should focus on the engineering. Right? Standards are extremely important. We try to avoid anything proprietary where we can, and has to be API enabled, meaning it's a web service architecture. Right? So we try to avoid desktop applications where we can. Everything is web enabled and in the cloud. So Jupyter, for the ones who don't know, is a huge project. It has more than 10 million users worldwide, and it's an interactive browser-based environment, which kind of everything you see in the browser, but its compute is done remotely, which is very convenient because you can scale it nicely, and it has a huge environment for all kinds of applications and languages. SysMLv2, we think is a key factor, or will be a key factor once it's will be published. In particular, because we have it's a new model that's not constrained by UML with ground-informed semantics. It has visualizations based on view and viewpoint paradigm. But most importantly, it also has a standard API to access that model. Right? It has an equivalent textual and graphical notation. And it's supported in Jupyter. So you can create your system models in Jupyter, visualize them, publish them, query them, validate them. So that is one key element that we see. FMI, FMU, probably many of you know, is an important factor here to kind of have or create end-to-end co-simulation co-simulations, and we are using more and more of that, in particular with multi-physics and the integration with functional modeling. Conda is, not sure if it comes from the Python world, but it's a package managing dependency environment, and we think that Conda will enable to help to manage all those dependencies. For example, if you have model libraries, whatever they are, to pull them together so you don't have to find the right version which works with your version and so on, and enables model reuse and the sharing of those models, in particular in relation to SysMLv2. So the dream car of the next generation system engineer is kind of this combination, right? The Jupyter in the center, FMI, FMU, Modelica for multi-physics, Conda for management of the package structure dependencies, and SysMLv2 for systems architecture and design, and OpenMB kind of pulling the things together to produce those engineering documents, or system engineering documents that are connected directly to the engineering work, right? They're not disconnected. And to come back to that diagram, so we have the Jupyter, the Modelica, FMI, and the little monsters that we are beating up with the dragon. Thank you very much.